It is a real pleasure to be here, and wow, there is a lot of people in this room. This is awesome. I'm very excited. I have given many talks over the last sort of 7 or 8 years since I've been doing this, but it's not often I get to do a brand new talk. So I don't know whether I should have told you all this, but this is a brand new talk that I haven't practiced because I wanted to do something that linked to the theme. I love the idea that we have this theme of codes running through the lecture series, and I really wanted to speak to that theme and try and interpret it as a mathematician, and in particular as someone who works in mathematical modeling. So it's kind of going to be a little bit of a sort of a run through history of some of my favorite mathematical models, and the idea being that, from my perspective at least, mathematics, equations, mathematical modeling is one way that we can try to understand the code of the universe. So the universe exists, things happen, we want to understand them as humans, and mathematical modeling gives us a tool and a way to try and do that, to try and sort of unpick that code. And that's kind of the theme that I've gone with, and that's what I'm going to talk about for the next 55 minutes or so. And I thought I would start, when my clicker works, there we go, with a sort of example of why mathematics might be a good way to uncode our universe. So some of you may recognize some of these images. This is the Golden Voyager record, which was sent into space in the 1970s, which was sort of a selection of songs from around the world that were seen as a way to communicate the variety of life on Earth and sent to other potential alien life forms around the universe. And also shown on the right of the screen is the Arecibo message, which again was sent out in 1974, communicating various bits of knowledge that we have discovered as humans, including you've got the numbers at the top, atomic numbers, we've got formulas for DNA, a sort of this lovely cartoon of a human shown there. But there's sort of, to me, when I look at this, I see this idea that we, as humans, have decided that perhaps using mathematics, using equations, might be one way that we can communicate with other life in the universe. Perhaps the mathematics, the equations, the numbers are this commonality we might have with other life forms. So that's sort of my argument as to why maths and modeling might be a good way to sort of decode the universe. But then, as I was thinking about this, I then remember when I first got into communication, I was very fortunate to interview Professor Ian Stewart. Oops, I've skipped too many slides there. There we go. I was fortunate to interview Professor Ian Stewart. He's a mathematician at the University of Warwick. And we talked about this concept of, is maths the best way to communicate with other life forms? And I'll let you basically read what he says on the screen. But he sort of said, well, the maths that we have, the way we interpret the universe and our world, is very closely related to, our planet. So this idea that, close on the surface of the Earth, basically our planet is Euclidean. Everything is kind of like straight lines. But if you zoom out, then you begin to bring in curvature, and the Earth is no longer flat. And as he mentions here, if you are an alien life form that has grown up on a gas giant like Jupiter, maybe talking about triangles and squares and straight edges makes no sense. You're like, I don't get that. But possibly understanding Navier-Stokes, one of the great unsolved problems currently facing mathematicians, maybe that makes sense if you grew up on a gas giant planet. And so I just thought this, again, a potential interesting counter-argument to whether or not our maths is the right way to decode and interpret the universe. Okay, so as I mentioned, I wanted to sort of go through history, pick out various mathematical models and ways we have tried to use maths to understand our universe. And I'm going to use this brilliant resource. This is called the Timeline of Mathematics, on a website which is called Mathagon. Really fantastic free resource. And it shows various mathematicians and results throughout history. So we're going to go back to some of the first sort of bits of mathematical modeling in ancient Greece. And in particular, we're going to focus on Plato. And we're going to look at one of my favorite mathematical models. And this was Plato's attempt to understand the universe and to model the universe. And it actually starts with some shapes which are named after Plato. And these shapes will satisfy a series of 3 rules. So in order to be considered as one of these shapes, you must first of all be a 3-dimensional shape. So these shapes are called the Platonic solids after Plato. So in order to be a Platonic solid, you must be 3-dimensional. So we want something that's not flat. We want it to have that 3rd dimension. The second rule is you want every face that's on your shape, we want to be the same particular shape. So if one of them is a square, we want all of those faces to be squares. If one of them is a triangle, we want them all to be triangles. And then the third one is a little bit more technical. We want the same number of faces to meet at each corner. So if at one corner of the shape there are 3 squares joined together, then at any other corner there must be 3 squares joining at that corner. And now with these 3 simple rules, and this is why they fascinated Plato, there are actually only 5 shapes that satisfy these 3 rules, which to me is quite amazing because they feel very general. They feel like there's a lot of variability in that. And this is, again, what fascinated Plato, the fact that you can prove, and I'll very quickly show you how you prove it in a minute, that there are only 5. So does anyone know what some of those 5 might be? Yes, the cube. Okay, that's going to come up second. I need the one before the cube. Okay, good, right. So the joys of having a PowerPoint slide that must go in order. So the first one is the triangle-based pyramid, or the tetrahedron. So you've got 4 triangles, 4 triangular sides. At the corner there, you can see there's 3 triangles joined, and that will be the same at every corner. So it does satisfy all of our rules, and obviously it's 3D. Then we've got the cube. Again, squares. There are going to be 6 of them in total, 3 of them joined at every corner. Next. Octahedron, yeah, very good. So we're counting up in number of faces. So the octahedron has 8 triangular faces, and at each corner, 4 of them join together. So an octahedron is basically 2 square-based pyramids stuck together. It's a way to think about it. There are 2 more? Yeah. Dodecahedron, very good. So the dodecahedron has pentagon-shaped faces, so 5 sides, and there are 12 pentagons in total, and at each corner there are 3 pentagons joined together. And then the last one. Yes. This is good. I don't think I've ever had an audience so knowing them all in order. Brilliant. Right, so the icosahedron. So this is 20 triangles, and at each corner you have 5 of those triangles joined together. And this is it. And it actually, interestingly, wasn't Plato that proved there were only 5 of them. It was actually a Greek mathematician called Theaetetus. So really, they should be called the Theaetetan solids, which I think is a much, less catchy name. But he was the one who actually showed that there were only 5. And he did it by looking at the angles. So again, I will quickly just explain how this works. So if you open them all out and look at their nets, so if you concentrate on one of these corners, so for example, I think the first one I'm going to highlight is the cube. So if you look at the total angle that's at a corner there, you've got 90 plus 90 plus 90, but 270 degrees. Now, if you only have 2 square faces joining, you cannot make it 3D, because you either stick them together that way or that way. So it's not 3D. So you need a minimum of 3 faces joining at a corner to make it 3D. But you can't add a 4th square, because what happens if we add a 4th square? It goes flat. There's 360-degree angle, it's flat, so you can't, and then obviously you can't put more in. So you can't actually build anything else with squares, right? Because you need at least 3 to make it 3-dimensional, but if you get to 4, they don't fit. So the only 3D solid, satisfying our rules, that you can make from squares is the cube. So then you say, okay, well, what about pentagons? Let's go up to the 5-sided shape. The angle in a pentagon is 108 degrees. So you have 324 degrees at that corner. So again, you can't fit a 4th one. And we're not allowed to have another shape because all the faces have to be the same shape. So you can't build anything else with pentagons. Hexagons. What's the angle at the corner of a hexagon? Good, 120. So if you put 3 hexagons together, you get 360, it's flat. So it doesn't work. It doesn't satisfy rule number 1 about being 3-dimensional. So we can't use hexagons. And then if you went to a 7-sided shape, you can't fit 3 of them together. It's more than 360 etc., etc. So the only one that's left is triangles, and that's why there's so many of them made of triangles. So you've got your tetrahedron, has a total angle of 180. Your octahedron is going to have a total angle of 240. You put 5 of them together to give yourself the icosahedron, which is 300. If you add number 6, it's flat again. And so that's kind of what the Theaetetus did. And then Plato comes along and is like, these shapes are incredible, they're beautiful, they must have some deeper meaning in the universe. And this is where the modeling comes in. And so he says, right, these have this incredibly important meaning in the universe, and there's only 5 of them. And the universe is made of 4 elements. First little hiccup in his problem, right? But, you know, Plato is known for being quite creative. So we've got fire, we've got earth, we've got, don't know which one's going to appear next, water, and we've got air. So this should have possibly suggested this wasn't a perfect model and perfect theory. But Plato decided, well, let's create a 5th element, call it the heavens. So now the universe is made of 5 elements. And Plato's theory, his mathematical model, is each of those elements is made of small pieces, and those small pieces are one of the Platonic solids. So there's 2 ways of looking at this. First of all, you could say that's ridiculous, but also you could say, well, it's kind of true, right? The universe is made of lots of smaller pieces. We just now would call them atoms and molecules, and they definitely do have shapes. So it's not a million miles away, 3,000 years before we sort of get to where we are now. But what I want you all to do, and this is your first interactive task of the evening, 5 shapes, 5 elements. Which shape is which element? I'll give you a minute. I actually want you to talk about this, figure it out, and I'll show you the answers according to Plato. So these are going to need to be in order as written on screen. So who would like to tell me which one is Earth and why? We'll have to do a raising hand for this. Who would like to tell me which one they think Earth might be? Okay, why do you think the cube?
Because I can imagine building a really solid stuff.
It's like Plato is in the room with us. So the cube can be used to construct objects. You use the ground, you use the earth to build things. So yeah, pretty easy. Fire. Tetrahedron, that's also correct. You're very good at this. Any idea why? It's pointy. So according to Plato, fire is sharp to the touch, is the phrasing. And so therefore must be made of the pointiest, the sharpest of the shapes. So fire is clearly the tetrahedron. Water. Okay, so we've got to vote for dodecahedron. It's not the dodecahedron, though that one is always popular for water. Have the other 2 any ideas? It's the icosahedron. So it's the icosahedron because the 20 sides of the icosahedron mean it is the most round of the shapes. So a lot of people will actually guess the dodecahedron because they think it looks the most round, but the one with the most sides is going to be closer to a sphere. So if you imagine the 2D version, as you add more and more shapes, you go like hexagon, octagon, etc., it looks more and more like a circle. So it's the same thing in 3D. As you add more faces, it becomes more round. So water flows, so therefore should be the roundest object, again, in Plato's universe. Which leaves 2. Now, I'm actually going to read this because it's quite fun. So according to Plato, air is made of the octahedron. Its minuscule components are so smooth that one can barely feel it. Sure. I mean, he missed a trick here because that then means that, of course, the dodecahedron is the heavens. But we have a 12-sided dodecahedron. So what should he have said instead? Why is 12 important for the heavens in ancient Greece? There are the 12 gods of Olympus. So he completely could have argued that the dodecahedron is the heavens for the 12 gods of Olympus, and therefore, by process of elimination, air is the octahedron. Of course, this is all complete nonsense, but it is an example of a mathematical model going back several thousands of years about the ancient Greeks trying to understand the universe using a mathematical model. Okay, and there is going to be a recurring theme throughout this talk because in the interview I had with the Darwin Communications Office before this, they sort of used one of the quotes or whatever to talk about how I will be wearing the lecture on my sleeve in reference to my mathematical tattoos. And so I do have the Platonic solids tattooed on my leg. So I will be showing you some photographs of my tattoos throughout the talk as well. These are why these are my favorite models. Okay, so I'm going to jump forward in history a little bit now to, what's this, around the year sort of 1300. Some of these names you may recognize, some of them you may not. There is a very, very famous name in the middle, which I'm sure probably most people in this room have heard of, which is Fibonacci. And again, the Fibonacci numbers, you may think are just a neat sequence of numbers, this idea of you get the next one by adding the previous two. But they came about, or at least when Fibonacci first wrote about them, from a mathematical model. And it was a mathematical model for breeding rabbits. And this is what the model was. So you start with a pair of breeding rabbits. And the rules of the model are as follows. So after 1 month, the rabbits will mate. And then it takes a further month for a new pair to be born. So they mate, and then you produce 2 offspring. So at the end of the 2nd month, they produce another pair of rabbits. So we now have 4 rabbits in total, or 2 pairs. I tried to color code it, so the green box is just the same one. Right? They have survived, and their offspring are in yellow after 2 months. And then the rules of this model, again, posed by Fibonacci, are that the rabbits never die. And this is classic mathematical modeling, right? Make unrealistic assumptions. Rabbits never die, and they're going to continue to breed forever. And then the question he posed was, how many rabbits are there after a year? So we're not going to quite go as far as a year, but we can go through 3 months and then 4 months. And I'll let you figure out the answer to the 1 year one, and you can tell me about it later if you want. So we have, after 2 months, we now have 2 pairs of rabbits. Now, after 3 months, we're actually going to have 3 pairs. So we have the original pair in green, have continued to survive, but then they've now had a 2nd pair, because it takes a month for them to kind of, let's say, develop to then be able to breed. That's the model of Fibonacci. So they've now had a 2nd pair of offspring, which is why you have the 2nd yellow box, but then the ones from 2 months, they're not old enough to mate yet, so they just drop down. So you've got the 2 from 2 months, the 2 of them move down, and then there's a new pair from that original starting pair of rabbits. Okay, now 4 months, we end up with 5 pairs, because what's going to happen now is you've got 3 pairs from 3 months, so they all come down. Rabbits can never die. But now you've got another pair from the very, very first ones at the top, plus the yellow ones at 2 months have now produced their offspring, which is the red box. So sort of they're the offspring of those particular rabbits. And so now you've got 5. And then you can begin to sort of continue in this way, and you realize that 5 is actually the sum of 3 plus 2. 3 is the sum of 2 plus 1, and this is how the Fibonacci sequence is developed, where the next one is the sum of the previous 2. But I didn't actually know about this until quite recently, that this is where the Fibonacci numbers first came from. It was a model for breeding rabbits to actually come up with this sequence of numbers, and now, of course, they're discussed in all kinds of other situations around numbers of seeds in sunflowers, et cetera, et cetera. Okay, so shooting forwards to sort of this very, very active period, 1700s, 1800s, sort of the Renaissance period. We really developed the tools of calculus, developed all kinds of other scientific techniques, mathematical techniques, instruments for measuring things, and really sort of push forwards our knowledge and in particular our models of the universe. And this led to sort of thinking about a question, which is to say, well, will we ever actually decode the entire universe? Will we ever reach a point where we can say, like, physics, mate, completed it? We have solved physics. We have solved the universe. We've got it all. We've got all the models. And it's interesting because this sort of happened in about the year 1900. And I'm sorry, Lord Kelvin. But supposedly this quote is attributed to Lord Kelvin. There is nothing new to be discovered in physics now. All that remains is more and more precise measurement. Now, it's, you can, it's quite entertaining to sort of laugh at this now, but it was actually a very, very valid viewpoint in the year 1900. Because, we'd had the tools of Newton and calculus and everything else for the last sort of couple of 100 years. Newtonian mechanics works on everything that we can see. Right? Newton's laws of motion explain pretty much everything that we interact with as humans. definitely at least in the year 1900. There were just a few little problems that remained back then. So the first sort of slight hiccup, and again, Lord Kelvin attributed this to we need better measurement techniques. The first sort of slight hiccup is Mercury's orbit. So with the tools of Newton, and I now teach this to my first year students, you can calculate the elliptical orbit of a planet, and it works for all of the planets like perfectly except Mercury. It's like 99 point something% accurate. So you might say, well, it's just because our telescopes aren't quite good enough. If we get better telescopes, we can measure the orbit of Mercury that little bit more accurately, and it will match the model. Because why else would there be a problem? So that's the first sort of issue that we just thought was due to that. And then another one that's a little bit more technical is in an idealized black body, it would actually absorb, according to our understanding in 1900, it would absorb light at all wavelengths, and therefore would have an infinite amount of energy, which sort of just doesn't really make sense. But you think, oh, well, everything else works, it's fine. So it turns out to solve the first problem, we needed an entire new model of the universe. Does anyone tell me what that model might be? Yes, relativity, right? So the work of Einstein, relativity. So the reason Mercury's orbit doesn't work is if you draw the ellipse on a flat piece of paper, it doesn't work. But if you draw the ellipse on a curved piece of paper, because the sun is so massive, it curves space itself. And then you draw your ellipse, it's perfect. So you needed that kind of modification and that new model, which is general relativity and the work of Einstein. And then for the second problem, anyone have any idea how we fix? Yes, exactly. So rather than absorbing all possible wavelengths of light, it's this idea of quantum theory. Light is absorbed in quanta of energies, which is where quantum theory comes from. So light is both a wave and a particle, as represented by this lovely diagram. And therefore, if you sort of say it's just absorbed at these certain wavelengths, it kind of fixes this problem, and everything is okay again. But of course, relativity and quantum are basically the two biggest pillars of physics today. So how much has it changed in the last 100 years from when we thought we had completed physics to where we're at now? So I think that's just a really interesting, to come back to that question I mentioned at the beginning of this section and saying, well, will we ever have the full code of the universe? Will we ever fully understand it? I'm going to come back to that right at the end, but it's an interesting question to think about. So I think, I forgot I was going to do this. Okay, I felt like I needed more maths in the talk at this point. So here are Maxwell's equations. I wanted to show this off. This is my favorite bit of mathematical theory I think I've ever had the pleasure of teaching. And I teach this in the vector calculus course with the first years. So this is actually how a piece of maths sort of helped shape the direction in which physicists went and helped shape the theory of physics. And the idea is we have these equations, they're called Maxwell's equations of electromagnetism. This is them in a vacuum. For those of you who might be wondering, there are some missing terms. And this tells you how your electric field, E, is related to the magnetic field, B. So they are just mathematical equations. But now you can do some interesting, and again, this was kind of verified through experiments that Maxwell and other people were doing around the time. And now you can do some interesting mathematical manipulations to these. So ignoring the physics, you're like, this is just an equation. I, as a mathematician, can do some stuff with this following the rules of maths. And what you can do is you can sort of take the complicated equations on the right, the slightly more difficult looking ones, and you can take the curl of those equations. And again, this is very much for the mathematicians in the room. You take the curl of those equations, and you use this identity, which tells you it's the curl of the curl identity. And when you use this, you'll notice we've got this thing here, the divergence of A. But if I then do this, I'm going to get a curl of E, curl of E from here. But then I can substitute that and replace it with this, but grad.E is up here with 0. So basically, this term disappears, is the point for both of them. So you do this mathematical manipulation, and you get these equations. And then as a mathematician, you look at these equations, and you say, I recognize those equations. That's what we call the wave equation. And we know that anything that satisfies the wave equation is a wave. And also, we know that this term here is 1 divided by the wave speed as well. That's just how the wave equation works. So then you substitute in the numbers for mu naught. You can measure this experimentally. We knew this back then. You substitute in the number for epsilon naught, and suddenly the speed that you get is the speed of light. So the mathematicians have just done some fiddly stuff and been like, light's a wave. It's like electromagnetic waves. That's why they're called EM waves. They satisfy the wave equation. But that happened from doing cool maths, doing manipulations mathematically, and then going and speaking to your physics friends and being like, you should test this, because the math seems to suggest that light is a wave. So maybe go and look into that. Of course, you still need the physicists to do the awesome experiments to actually verify this. But I just really like this idea that you can just play around with mathematical equations and then sort of, having to work with your colleagues, of course, to make sense of what the outcome means, but then actually can lead to new understanding, new physics, new mathematical models. And of course, I have an equation of those on my arm, as shown there on the left-hand side. All right, so now we come to the present day, modern mathematics, modern mathematical modeling. Unfortunately, I am not on there, so I'm just going to add myself down there. Maybe one day I will make it onto the timeline of mathematics. And I'm going to introduce the sort of some of the work that I did as part of my PhD when I was here a few years back now. So we're going to look at ocean pollution. This is a plot of the concentration of plastic in the ocean. So you've got 4 different sizes of plastic, as shown by the figures. So obviously here it's between 1/3 and 1 millimeter, and this is going up to greater than 200 millimeters. And then as it gets closer to orange and red, that means more plastic. So, this is the Great Pacific Garbage Patch, which you may have heard about. It's this very, very large area of high plastic concentration in the Pacific Ocean. It's to do with ocean currents and things, why it all accumulates there. And it is, I have to think about this, it is 3 times the size of France, or twice as big as Texas. Which means Texas is bigger than France, which is a fun additional fact you get from that. It's massive, so it's actually quite depressing. But lots of good work is now happening. 10% of it has actually been cleaned up by a charity called the Ocean Cleanup. And the founder of that charity, Boyan Slat, he started this organization when he was only 18. They've been going for 10 years, and his goal is in the next 10 years it will all be gone. So, good things are happening in this kind of space. But I wanted to talk more generally about ocean pollution because, and I was mentioning this on the walk over actually, for my PhD, I was studying an interesting mathematical problem. There was no real motivation behind it. So it was introduced as, where does river water go when it enters the ocean? That was not the title of my thesis. The title of my thesis was an experimental study of the spread of buoyant water into a rotating environment. Right, much less catchy. But it does have this interpretation around river outflows, which only towards the end of my PhD did I realize could be very applicable to this issue of ocean pollution. I'm going to sort of try and do it in like 5 minutes, explain to you why. So the idea is, we came across this statistic from the National Oceanic and Atmospheric Administration, which says that 80% of pollution in the ocean is actually coming from the land. So the other 20% is, coming from ships or maybe condensing from the atmosphere, but the vast majority is entering from the land. It's not being dumped into the sea directly, it's being dumped elsewhere, but then ends up in the sea. So how does it get from the land to the sea? Rivers, in short. Whether it's rubbish washing into rivers or going through drains, sewer system, feeds into river system, which then enters the ocean. Whether it's farmers using fertilizers on their crops, seeps into the ground, enters the groundwater, which eventually makes its way into the river system. So however you think about it, it's sort of, this pollution is then getting into the ocean through the river system. And so therefore, if you're trying to understand the spread of pollution, particularly in coastal regions, then you can kind of just say, well, if we know where the river water goes, it's basically a proxy for where the pollution goes. And that's kind of the idea. And then I was like, so once I kind of thought about it in this context, I was like, so what really I've been studying is like a model for the spread of pollution from rivers once it enters the ocean. So how do you go about modeling that and thinking about this problem? Well, first of all, was to look at some real rivers. So this is a satellite image of the Amazon River. So the brown water is the river water. It's filled with mud, and the ocean is blue. So of course, normally, it's all just blue. Water is the same color, but here you can actually distinguish the river water from the ocean. So I'm going to just sort of highlight that in yellow to make it very clear. And then if you look at another river, so this one is the Connecticut River, which is in the United States. This very clearly does something different. So it comes in, and then it sort of swings to the right, as you can see here, like so. And then you look at another river, which is going to be in the southern hemisphere, the Verdigris River in Australia, and that one goes to the left. And so there's something kind of controlling the direction of your river water, which also means you're controlling the direction of your pollution that's coming from those rivers as well. And so this is going to be the Coriolis force. So the Earth's rotation in the northern hemisphere will push the river water to the right, and in the southern hemisphere will push it to the left. So you may have seen this with images of sort of hurricanes, large weather systems that form either side of the equator. They will rotate anti-clockwise in the north or clockwise in the south. But your plug hole thing is not true. Right? The plug hole myth, it's based on real science, but your plug hole would need to be like 100 kilometers across for it to feel the effect of the Earth's rotation. So the initial conditions are much more important in the plug hole situation. And I had a very, let's say, interesting conversation with a street performer in Ecuador who was stood on the equator and was showing me that the water went in different directions, one step either side. And I was like, you do not know who you're talking to, my friend. So that was kind of fun. So yeah, so it's based on real science, it's just not actually true. Anyway, so rotation's really important, is the point here. And so the experiments that I was doing in the infamous underground lab in the maths department were with this large tank, which is on a rotating turntable. This is basically a fish tank. It's like a meter square, about 60 centimeters deep. I'm going to fill this with salt water. And then from the top, so there's like a bucket off the screen, and then there's a pipe here, shown sort of in this diagram. That's going to feed in the fresh water, which is going to be the river water. So again, the technical title was buoyant outflow. That's because the river water coming in is less dense than the salt water. It's lighter, so it'll be on the top. So it's a buoyancy-driven flow, but the whole thing rotates, and rotation plays a really key role in that. So I did about 800 experiments over the 4 years, and I was varying the parameters. So I was able to control the rotation rate, so how fast the tank rotates. I could control how much water was coming in, which is going to be labeled with Q. So that's like the size of your river, right? So very, very big river versus very small river, the amount of water in meters per second. And also the, I've called it here the ocean density, but the technical term would be reduced gravity. But pretty much fresh water is a consistent density. So what matters here is the density of the salt water. So I could add more salt or less salt to the ocean to model different situations. So I ran all of these experiments. I'm going to show you what one of them looks like. So this is going to be similar to the satellite image. We're expecting this to turn to the right. We're modeling this as though it's the northern hemisphere. And it's viewed from above. The salt water is black, and the fresh water as it comes in, I can dye this red with food coloring. And so you're going to see that as red and then yellow as it comes in. So when I press play, you'll see it comes in, immediately turns to the right, crashes into the side. You'll notice now it kind of looks like the image, which is lovely. And then begins to progress along the coast. Of course, there are corners in my tank, so it goes around those corners, but that would just be progressing along the coast in this kind of real-world setting. Now, if again, this is interesting to a fluid dynamicist, to a mathematician, to a physicist, but in the context of ocean pollution, it's also quite a big deal, because if you take the scale of your river mouth here to be like, potentially 10 kilometers, this is like hundreds of kilometers along the coast in a reasonably short time scale. And so this is kind of a problem, because you're seeing, if the pollution remains concentrated around the river mouth, I mean, kind of obvious. If pollution's coming from rivers, go and clean up the river mouth. But here you're seeing it escape, and move along the coast, possibly several hundreds of kilometers, to neighboring cities, to maybe neighboring countries who don't really care about cleaning up the ocean and the environment. And so you can kind of see, understanding the properties of this current would be quite important. So the actual mathematical modeling element now, we would like to understand the speed at which this current is moving, so how fast is the pollution being carried along the coast. We'd like to know how deep this current is, so is it the top 10 meters, is it 100 meters deep? Imagine you have to go and clean up this area. Do you need a 100-meter net or a 10-meter net? It's a very big difference in cost between those two things, so it'd be helpful to know this. And also, how far away from the coast is this going to extend, right? So, is this the order of like 1 kilometer or is it 10 kilometers? Because again, you're going to sort of zigzag your boat through that area, collecting all of this pollution. So these are the kinds of things you might want to work out. So then for the mathematical model, we are going to call on the aforementioned Navier-Stokes equations. So Navier-Stokes sort of are these beautiful very complicated mathematical equations which describe the behavior, the properties of anything that behaves like a fluid. And I'll come back to that definition in a moment. But here's what they look like.
Dude, this is a first for number 5.
On the ribs as well. The pain.
I told you it was
ribs,
a theme.
I'm going to say this is complete commitment to Navier-Stokes and fluid mechanics.
Why did you do that?
Well,
Question I ask myself every day. All right, so these are this is the incompressible Navier-Stokes. So this is the ones you would use for modeling a fluid such as the ocean. So I'm showing this version. There is a slightly more general version, but this is the one I have the tattoo of. So to give you an idea for the non-mathematical people in the audience as to why these are difficult, complicated, why we don't really understand them, I like to sort of just demonstrate the range of situations that they model. Okay, so I'm going to go through 4 or 5 examples of situations modeled by these equations. And if you think about how different these situations are, I think it just gives you a feel for the potential complexity that's hidden within these equations. So anything that is a liquid, I'm talking here about oceans, we would classify as a fluid and would be modeled by Navier-Stokes. Now, the sort of scientific definition of a fluid, or at least the one that I use, is a fluid is anything that changes shape to fill its container. So you have something that will spread out and change shape to fill its container. Then, in theory, it can be modeled by Navier-Stokes. So we've got anything that's a liquid, but also gases, so the atmosphere, climate models, clouds, they all can be understood through Navier-Stokes equations, because of course a gas will spread out to fill its container. Also some things that you might regard as solids, so ice, flow of ice sheets in glaciers, you have to slightly modify the equations from the ones I showed you, but it's still a version of Navier-Stokes. And also one of my favorite examples, which there is a research group here in Cambridge, I believe, still working on this, sand and sand dunes. Because again, sand will spread out to fill your bucket when you scoop it up. And will behave like a fluid and therefore follow and be modeled by the Navier-Stokes equations. So we've got liquids, we've got gases, we've got some solids. Is there anything else that changes shape to fill its container? How about cats? I would argue they are changing shape to fill their container, and therefore could, in theory, be modeled by the Navier-Stokes equations. Real piece of research, naturally. I recommend this. It's about a 4-page paper, freely available. Great piece of work by a French mathematician who was trying to discover if a cat is a liquid or a solid. It was the research question. So we have these equations. They're complicated. They model solids, liquids, gases, cats, amongst other things. So what we do is we make lots of assumptions. We make lots of simplifications, as you do with any mathematical model, to try and actually get to a point where you can solve it and get some equations out. And in this particular case, what you can get for this pollution model is you get the following equation for the pollution depth, or the river current depth. You get this one for the width, and you get this third one for the speed or the velocity. Now, potentially look scary to some of you, but there's actually just some numbers there. You're taking them to a power, and you've got three variables. So you've got the rotation rate, given by F, which is actually the Coriolis parameter. You've then got Q, which remember was the discharge rate or the size of the river. And then you've also got G prime, which basically represents the ocean density. So you have this is a first order model, but it's very usable. And I think this is an important aspect of mathematical models. They need to be practical, they need to be usable. And just to demonstrate how usable this one is, I did this earlier for the River Thames. So the River Thames is apparently 4.5 stars on Google from 2,462 reviews. Don't know who is reviewing the River Thames on Google, but who am I to judge? So I looked up. This is the Wikipedia page. So this will give you the coordinates, which allows you to work out the Coriolis parameter, which gives you this value for F. I then looked up the discharge, which is also on the Wikipedia page. And then looked up a density map of the North Sea, which then gives me the value for G prime of 0.34. So putting all this in, because the point of a model is to get information from it. In a way, that's how we use models today. So putting all this information in, the River Thames, the pollution that's leaving this is approximately 1 meter deep, this sort of current. It extends 5 kilometers away from the coast. And it's moving at about 0.1 meters per second. And so if you sort of were to draw this on the map, it would kind of look like this, approximately to scale as much as I could do with my iPad and a pen. So if you're going to go swimming in the ocean around the east coast there of London, I would recommend avoiding Margate. I've never been, and sorry if anyone is from Margate. I always feel bad when I tell people don't go to Margate. I'm sure it's lovely, just probably don't go swimming, because all of the pollution that's leaving London is actually going to be concentrated around there. But on the other side, if you wanted to go and clean up the pollution coming out of London, this is where it's going to be concentrated, and then you can go in and actually maximize the resources you have available, be as efficient as possible in terms of cleaning up that pollution. Okay, so again, that was a little bit more detail on a specific model, because that's the one I studied for 4 years. But I also thought I would just briefly mention other big models that are trying to be used to solve big problems in the world today. So of course, climate models are very, very important in understanding our changing climate and predicting what might happen in the future. So this is just a chart showing global mean temperature predicted by 6 different models. And as you can see, they all have different ranges, depending on different things happening or not, in terms of reducing emissions, fossil fuels, etc. But the way we try and advise those policy decisions is through mathematical modeling. We try and say, okay, if we all stop using fossil fuels today, what does that mean for the future? And it's actually mathematical modeling that allows us to make those predictions, or to try to make those predictions for what might happen in the future. We also, probably no one wants to be reminded, but we saw a lot of mathematical models during COVID. This was the famous one from Imperial College back in the start of 2020, which talked about the number of cases and hospital beds, et cetera, et cetera. So again, we saw how they were used rightly or wrongly, depending on personal opinion, but they were used to inform government decisions. Or at least they were suggested to the government that they could use them to inform decisions. So, we've examples of big world problems and how mathematical models can be used and are being used to help make those decisions and shape the future. But what about, on a more personal level? Is there a mathematical model for love? Right. Obviously, the answer is yes. You can model this. So this was first time I came across this was actually from Hannah Fry, who obviously just recently joined the university, which is awesome. Looking at this from the perspective of something called optimal stopping theory, which basically says you should date some number. So you decide how many people you want to date. So just to make it easy, let's say it's 100. And you're like, in 100 people, I can find my perfect partner, right? So you have to fix the sample size. And then what optimal stopping theory tells you is the first 1 divided by E proportion of them, which is about 37%. The first 37% are your test subjects. So you just date all of those first 37 people, and you score them. And then as soon as you go from 38 onwards, as soon as you have somebody who scores higher than anyone in your test group, that's your person. So that is how to mathematically date, right? You don't have to do 100, you could do 10, right? It was probably more reasonable, and then you do 3 or 4 as your test. So again, a mathematical model exists. We're trying to understand, the most human of emotions, love and dating. As a avid sports fan, I'm more interested in, why England are terrible at penalty shootouts. So the England win percentage in penalty shootouts is 30% compared to Germany, who are on 86%. So I would like to know why. Is there a mathematical model that explains this, or is there a mathematical model that we can use to be better at taking penalty kicks? And it turns out there is, and I'm going to explain it in the next 5 minutes. So, I've skipped it now, it's fine. Okay, so starting point is a study that was done by a mathematician at the University of Bath called Ken Bray, and they looked at the area of the goal that is protected or covered by a goalkeeper. So the idea here is you've got your rectangular goal, and on average, in that half a second between the ball being kicked and going into the net, you have half a second to react. How far can a human move in half a second? And on average, they can cover this as the diving range. And they did this with an actual professional goalkeeper, so it's hopefully relatively accurate. So you could say, well, you probably want to aim outside of that diving range, because that's the bit where the goalkeeper can, in theory, react. And the data backs this up. So if you look at penalty kicks across the world, not just England, in the middle, your probability of scoring is 0.5, according to the data. And if you aim outside of the diving range, your probability increases to 0.8, or 80%. So straight away, it's a more difficult shot, but we're talking about professionals who have spent their lives playing football, and so they should be able to actually make that shot, and if they put it in that corner, the goalkeeper isn't going to get there. So that's why it's as high as 80%. But of course, we can go even further, right? We don't just want to say aim for the corner, we want to know the exact point. So we turn it into a geometry problem, right? We mathematically model this. So you've got the goalkeeper's diving range in the middle, which is a semicircle. You've got the goal, which is your rectangle, and we know these measurements. So a goal has a standard size, so that's the numbers in green, in meters, and then the diving range of the goalkeeper we've established through these experiments. So you want to actually pick a point to aim for at the side of the goal. Either side is fine, but you also want to allow a little bit of error. Because even the world's best player, even if you took Lionel Messi, he could aim for that spot, but it's not going to hit it perfectly. You kind of want a little bit of a safety zone, a little bit of a buffer around that. So really what you want to do is add the largest possible circle into that space. So you put it at the top because the circle will be larger at the top than if you were to put it at the bottom. So this is kind of your target, and therefore the perfect place is the center of that circle. So now this is fully just a sort of GCSE maths homework question. Can you find the value of r at the center of the circle? And you can. So we use Pythagoras' theorem, going back nicely to the ancient Greeks. So you add this diagonal because they're both tangent, so that's 2.86 plus a radius. We've got the height is 2.44 minus a radius, and then you've got the distance on the bottom is 3.66 minus a radius. So now you've got Pythagoras' theorem, which tells you the distance on the bottom squared plus the height squared equals the diagonal squared. You expand that out, it turns into approximately this equation, which is a nice quadratic, and then you can just solve that with the quadratic formula, and you get the answer of 0.65 meters for your radius, which means you're aiming 65 centimeters inside the post and about 1.8 meters above the ground. So if anyone wants to practice this, get your 6-foot-tall friend to stand with their hand on the post and try and hit them in the face, basically. Or if you're a younger student, get your teacher, and then you might have more motivation to aim for the spot. And here's me trying to do it. So all I have to do to maximize my chance of a successful penalty kick is hit the ball through this hoop. Easy, right? I'm actually a little nervous. Oh. Oh, nope. Ah. Ooh. This is the one. Oh, I knocked the hoop out of place. This really shouldn't be that hard. This one. For maths right there, straight through the hoop. So I actually got it in like the third shot, but we obviously needed to film more to create the dramatic effect. So, you know, because I feel like that makes me look like I'm terrible at football. I take penalties for my team, so anyway. Okay, now I am coming just towards the end. So I've mentioned all of these different mathematical models we have, and so you might be thinking, well, if we have a mathematical model and we've sort of unpicked the code of the universe, we've decoded the universe, then surely we know everything. And this is actually a thought experiment from a mathematician, Pierre-Simon Laplace, from over 100 years ago. And it's now referred to as Laplace's demon. And I really like this concept. So the idea is you have this being which has fully understood the code of the universe and therefore can predict everything that will happen. Given that we have the equations, we have the models, we know the current state, and therefore everything just follows those models. Now, I don't know, I feel like this doesn't seem plausible, but it sort of follows logically from this idea of modeling and different things. But that is until, I think it was around like the sort of 60s and 70s, so not that long ago, when we discovered chaos theory. So my favorite example of chaos theory is shown here. So this is a double pendulum, and you can just about see there are 3 pendulums here, and they are like 0.1 degree separate in their starting position. So then you press play, and you think, okay, so we they behave, they all kind of look the same, right? We very, very slightly changed where they start, so therefore the outcome should only change a little bit as well. Is the sensible thing that should happen. Right, we have just very, very slightly changed their starting condition. Right, so this is an example of a chaotic system. So there are lots of definitions of chaos. I like this idea of saying if you have a non-chaotic system, you have 2 initial data points, and they are very, very close, your solution should be very, very close. It feels intuitive, and most things follow that rule. But as you can see, the double pendulum does not. It is a chaotic system. Very, very small change in the starting, crazy difference in the outcome. And I've got one more, so I have to do very quickly, which is to come back to populations. I talked about breeding rabbit populations. We also have models now for mathematical biology and populations of other species. And so one sort of starting point of a model is something called a Malthusian model, which just says the population grows as there are more people. More people to reproduce, so we grow. But then that's not that realistic, and so we add in something called a carrying capacity, which says if there are too many people, there's not enough resources, and so it starts to shrink again. But this is called the logistic map when you change variables. And this is also a chaotic system. So as you vary the value of R, and this next slide will show you where the population tends. So the population is kind of following the red line. It's tending to that crossing point. It's tending to the crossing point. It's kind of, oh, what's it doing? Oh, there we go. Chaos again. So even something as simple as like modeling a growing population actually leads to these chaotic dynamics. And again, I've got a tattoo of that on my arm. Okay, there's a model for Pokemon, because I said I would talk about Pokemon. And the point I wanted to make here is we've now reached the point where we're doing models of models, because somebody has coded and modeled the video game, but that's secret. So people playing Pokemon want to understand how to catch these creatures, so they have modeled the model. So we're kind of, yeah, this is where we've developed into the world. We are now decoding something that's been coded. And again, I'm sort of looking at this myself every day. I'm trying to decode the YouTube algorithm and figure out how that works. How do I create a video that will be seen by as many people as possible? And then, of course, Netflix is basically also is an algorithm, is a mathematical model that decides what you're going to watch. So this is an example of what gets suggested if you are a sports fan on your Netflix homepage versus if you are someone who's into romantic comedies. And then finally, we are of course now in the age of AI, so I thought I would ask ChatGPT to write me a nice summary slide. So again, this is where we are now with models. We've created models to recreate humans, right? We are like modeling humans. We are modeling intelligence at this point. However, I feel like some people sort of get worried about that. I am not worried as a mathematician because I actually gave ChatGPT some maths questions. And I just thought I'd show you a final 30-second clip of just to demonstrate that we don't need to worry. We're a long way away, especially from AI being able to actually do maths. Okay, it's a geometry one, so this is going to be a challenge, oh God. And it's a proof. It's really hard without a diagram. I don't know whether I could get it to draw a diagram. Shall we try that? Let's see if I can get it to draw a diagram. I mean, if it draws the correct diagram, yes. Oh, here we go. Here's a diagram. Oh. What is this? What is this? Perpenuncle. Perpenuncle cerbum circle. So many points labeled A. This is absolutely ridiculous. I love that it'll draw something, but what on earth is this? I have no clue what has appeared before my eyes. All right, and with that, I will end the talk. Thank you very much. Can I take a quick audience selfie? Okay. All right. Okay, smile, everybody. Awesome, thank you.
How on earth do you follow that? So I have to admit that until today, the words mathematics and fun did not go together for me naturally, but you've changed that today, as well as providing us with a fascinating, entertaining, and actually very valuable understanding of how maths can actually help us to begin to unfathom the code of the universe. So thank you very much, Tom. That was wonderful.